Okay, so this is question 1 on the foundation paper. It says here, a group of students investigate the terminal speed of a number of cake cases. They set up the following apparatus. They drop the cake cases from rest at a point 30 centimeters above the pointer. They measure the time taken for the different numbers of cake cases to fall 150 centimeters from the pointer to the ground, so from here to there. So they vary the number of cake cases, they drop it from here, they only start the timer here, and they stop the timer here. So the first question asks us, complete the sentences below by underlining the correct phrase in the bracket. So the first one says, in this experiment, the independent variable is the number of cake cases, the time of fall, or the height of the pointer. So we need to remember that the independent variable is the thing that the experimenter changes to see what happens. And in this particular experiment, it's mentioned a couple of times in the introduction. It's the number of cake cases. Okay, so different number of cake cases. So it's mentioned twice in the question. So that's what they change to see what happens. And if you weren't sure about that, you could leave it for a second, and had you moved on to the next question, then you would have noticed that the first column here, where anything changes, is the number of cake cases, and that would be another clue to the independent variable. It's always the first thing that changes. It's usually the very first column, but in this case, they've put the distance in the first column. Second part of this question asks us, in this experiment, the dependent variable is what? Okay, and so in the experiment, they were timing how long it took for the cake cases to fall. So in this case, it is the time of the fall. And then the final part, during the first 30 centimeters of the fall, the cake cases speed up, slow down, or fall at constant speed. And we can assume that in the first 30 centimeters of this fall, they are actually speeding up. The idea behind this experiment is that after those first 30 centimeters, they've actually stopped speeding up, and they've hit terminal velocity, the fastest that they can fall. Okay, so we're going to move on. And here we have some data from the experiment. So 5 separate groups in the class carry out the same experiment. The results are calculated values are shown below. So we've already glimpsed at this data. So we can see the first column is the distance that the cake cases fall. The second column we've established is the independent variable, the number of cake cases, and then for each of the different groups, we have the time it took for the cake cases to hit the floor, depending on how many there were. So it says draw a circle around the anomalous result when 4 cake cases are dropped. So we first of all need to identify what this means. It's in bold. Okay, so 4 cake cases is this row of data here. It's asking us for an anomalous result, and of course that is one that's out of place. So we've got 0.55, 0.56, 0.55, 0.75. Okay, so that one does look rather out of place. The next one is 0.58. The question then asks us to calculate the mean time for 4 cake cases to fall 150 centimeters. Now we need to calculate the mean of these numbers going across here, but having just identified an anomalous result, then we shouldn't use that in our calculation. So our calculation would be 0.55 plus 0.56 plus 0.55 plus 0.58. We don't use the 0.75, and then we divide all those by 4 because there are 4 values there. So if we use a calculator, which is something that you really should make sure you have with you in all your exams. So let's just ensure we get this correct. So 0.55 plus 0.56 plus 0.55 plus 0.58, and then it's always a good idea to press equals at this point, otherwise your calculator will apply BODMAS and then divide by 4. That gives us 0.56, 0.56, which is a reasonable result because it is similar to all these results here. Okay, so that's a way to check. And part C, use the table below to plot the data on the grid and draw a suitable curve of best fit. Now, of course, for 3 marks, then it is well worth getting graphs correct. And usually you get 2 marks for appropriate plotting and 1 mark for the appropriate line. Now, it specifically says a curve of best fit here. Okay, so we need to be careful that we do draw a curve of best fit, or a curve is what we're after. So the first data point is 0, 0. Okay, so put a nice bold cross on the 0, 0 point. And then when we drop 1 case, we get a terminal speed of 1.7 meters per second. So here we have the independent variable on the x-axis. That's 1 case, and then 1.7 is going to be there. 2 cases is 2.2, so 2.2 is here. 3 cases is 2.5. 4 cases is 2.7. And 5 cases is 2.9. So we can see starting at the 0, 0 point, there definitely is a curve. Okay, so I'll just move this down. And so the way to do a curve is to sort of put your hand in a position where you're getting the curve just about right. Have a couple of practice runs, and then in one bold move, draw the curve. Now you'll notice I missed that one. I'm not going to worry too much about that, because this is a curve of best fit. The very phrase best fit means you might miss 1 or 2 points. The data is not exact. And then the final question, sorry, on this part is, complete the sentence below by underlining the correct phrase in each bracket. So, as the number of cases increases, the terminal speed increases, decreases, or stays the same. As we go across here, these values are getting bigger, so that would be increases. However, the next part of the question says at an increasing, a decreasing, or a constant rate. Now this line is getting less and less steep the whole way up. Okay, so that tells us that this is a decreasing rate. Okay, if it was getting steeper and steeper, it would curve in completely the opposite direction, and if it was at a constant rate, it would be a straight line. Okay.